पिछले लेक्चर में मैंने आपको लैग्रेंजियन डेंसिटी, आयलर लैग्रेंज इक्वेशन ऑफ मोशन, मोमेंटम डेंसिटी, हैमिल्टोनियन डेंसिटी, इन सब के बारे में बताया था। एक्चुअली आयलर लैग्रेंज इक्वेशन फील्ड के लिए एक इक्वेशन ऑफ मोशन है। यदि हम सुइटेबल लैग्रेंजियन चूज कर लें किसी भी फील्ड के लिए और उस लैग्रेंजियन से जो डिमांडिंग वैल्यूज हैं वो ईएल इक्वेशन में पुट कर दें तो हमें उस फील्ड के लिए इक्वेशन ऑफ मोशन मिल जाता है। आज के लेक्चर में हम रियल और कॉम्प्लेक्स फील्ड के लिए लैग्रेंजियन डेंसिटी का निर्धारण करेंगे जिससे इन फील्ड्स के लिए इक्वेशन ऑफ मोशन मिल सके। तो सबसे पहली बात यह ध्यान रखना जरूरी है कि हमने जो पिछले लेक्चर में आपको बताया था उसको मैं एक बार रिपीट कर देता हूं कि दिस वाज योर लैग्रेंजियन या आयलर लैग्रेंज इक्वेशन ऑफ मोशन फॉर द फील्ड del curly L over del psi minus summation k equal to 1 to 3 del over del x k del L over del psi over del x k and minus del over del t del curly L over del psi dot this is equal to 0। ये इस EL इक्वेशंस की दूसरी फॉर्म थी जो कोवेरिएंट फॉर्म है। ये हम फॉर्म पिछले लेक्चर में डिस्कस कर चुके हैं। And this was your pi, which is equal to pi I dri. Pi I was the momentum density for the quantum field, and the Hamiltonian for the quantum field was h summation I curly hi dri, and curly hi equal to pi I psi I dot minus curly L. This was known as the Hamiltonian density for the field. Or today we will discuss about the Lagrangian density. First thing you have to keep in mind that there is an arbitrary choice for the Lagrangian density selection, and we select this Lagrangian density in a manner that we can get the appropriate equation of motion for the field if we use EL equation. So before going for the Lagrangian density of scalar and complex KG field, I am taking an example of the wave equation. If I choose the Lagrangian density for the wave equation, which is given by curly L equal to 1 by 2 mu eta dot square minus y eta del eta over del x ka whole square, then if this is the appropriate Lagrangian density for the wave, then by using this equation in EL equation, Euler Lagrange equation, we must have the equation of motion for the wave. So for this Lagrangian, the Euler Lagrange equation will be written in this form, because this is one dimensional. You see here this eta depend only on the x coordinates, so the EL equation will be del curly L over del eta minus del over del x del L over del curly L over del x minus del over del t or del curly L over del eta dot equal to 0. So this is the EL equation for this type of system having Lagrangian density in this manner. So if you calculate del curly L over del eta from this equation, then it will be equal to 0. And if you calculate del L over del x, here you have del L not del eta, then you have this del L over del x equal to minus y del eta over del x. And if you calculate this term del over del x, del curly L over del curly L over del x, then this will come out minus y del square eta over del x square. While if you calculate del curly L over del eta dot, then from this equation you have mu eta dot, and double derivative and its derivative with respect to time will be equivalent to mu del square eta over del t square. And if you put the value of del L over del eta and del over del x, del L over del eta over del x, and finally del over del t, del L over del eta dash in this equation, in equation number 1, EL equation, then you will get this expression. And we already know that this is nothing but this is the wave equation, and this denotes a wave, one-dimensional wave, which is propagating with the velocity square root of mu over gamma over mu. So you can say that this is the appropriate Hamiltonian for the wave motion, because on using this Lagrangian density we can have the wave equation. So similar, we will choose an appropriate Hamiltonian for real and complex KG fields so that we can have the KG equation for both fields. So first of all, we will discuss about the Lagrangian density for the real KG field. So this is the Lagrangian density for the real KG field, and different notations. This is one of the notation 1a, equation number of 1a, curly of L equal to 1 upon 2 c square del psi over del t whole square minus 1 upon 2 del psi whole square minus 1 by 2 m0 square psi square. And you can also write this equation in this manner, equation number 1b. In the notation of Sakurai, where you use the SI units, SC equal to 1, then you can write down these Hamiltonian in this form, 1C and 1D also. This is the covariant notation of the Lagrangian density. This is the time dependent part and this is the space dependent part. So most easiest form of the Lagrangian density is equation number of 1a. Okay, so if you choose Lagrangian density given in this equation, then you can find that momentum density pi equal to del L over del psi dot, and if you take this derivative of L, then you will have psi dot over c square. In some books you have only pi equal to psi dot, because in SI notation you can take c equal to 1. And so the Hamiltonian density, this will be h equal to pi psi dot minus L. Pi is equal to psi dot over c square. So if you put the value of pi in this expression, then you can find that the Hamiltonian density for the real KG field is equal to curly h equal to 1 by 2 pi dot pi square plus del psi square plus m0 square psi square. Now, so the complete Hamiltonian h equal to integration of curly h over the space, and this is the value of Hamiltonian for the real KG field. And the EL equation for such type of field will be this one, which we have already discussed in last 2 lectures. And if you put the value of del L over del psi dot, which is equal to minus m0 square psi, and if you calculate this term, then this will be equal to del square psi. And if you calculate del curly L over del psi dot, which is equal to psi dot over c square. If you put all of these value in this equation, then you will have minus m0 square psi plus del square psi minus 1 upon c square del psi dot. So this is nothing but you can write del square minus del square over del t square means psi double dot. This is dlambert, and which is written as del, and you can write this del minus m0 square psi. This is equal to 0. So this is your kg equation for the real kg field. Hence we can say that this is this one is the appropriate or correct Lagrangian density for the real kg field. In this manner we can find out the kg equation for this field by using EL equation. So now we will see the Lagrangian density for the complex kg field. Complex kg field amplitude psi represent the field of a charged particle. Keep in mind that real kg field is a field which represents the uncharged or neutral particles, while complex kg field is for the charged particle like electrons, proton, etc. If we take two real fields psi 1 and psi 2, then you can make a complex field by using this expressions as we shown here, psi equal to psi 1 plus I psi 2 over root 2 and psi equal to psi 1 minus I psi 2 over root 2, or from this you can have psi 1 equal to psi plus psi star by root 2 and psi 2 equal to psi minus psi star over I root 2. The real scalar field psi 1 and psi 2 are independent and can satisfy the kg equation del minus m0 square psi 1 equal to 0 and del minus m0 square psi 2 equal to 0. This is the method of making a complex field by using two scalar field psi 1 and psi 2. So this is a general discussion about the complex field which can be made up by two real fields psi 1 and psi 2. And if you choose the Lagrangian density for the complex field, so then similar to the Lagrangian density for the scalar field, you can write the expression for the Lagrangian density of complex field L equal to minus 1 by 2 del psi whole star minus psi dot star plus m0 square psi dot psi star equal to 0. Here we are taking c square equal to 1, means we are using SI units here. So the conjugate field or momentum density will be equal to pi equal to del curly L over del psi dot, or if you find this del L over del psi dot from this equation, then you will have psi dot star. And similarly for the other field pi star, this will be equal to del I over del psi dot square, which is also equal to psi dot. And Hamiltonian density, here the Hamiltonian density will be equal to curly of H equal to 1 by 2 pi star pi plus del psi whole star del psi plus m0 square psi dot square. So this is the Hamiltonian density for the complex kg field. And EL equation, for EL equation you have to calculate del L over del psi over del xk. Del psi over del xk means del psi this one. So if you calculate del L over del psi, then this will come out minus 1 by 2 del psi star. And similarly if you calculate del L over del psi star, then this will be equal to minus 1 by 2 del psi. And if we are using these values in the EL equation, del L over del psi minus summation del over del xk, del L over del psi minus del over del t, del L over del psi dot. If you use these values, this one, and this one also, then on putting the values you will have del square psi star minus psi double dot psi star minus m0 square psi star equal to 0, and you can also write it del square minus del square over del t square minus m0 square psi star equal to 0, or this is nothing but this is dlambert and this is equal to del. So dlambert minus m0 square psi star equal to 0, or this is the EL equation for one type of field. And similar you can find the EL equation by using psi in spite of psi star, which will be equal to del minus m0 square psi equal to 0. So by using this Lagrangian density, the expression of this Lagrangian density, you can find out the equation for the complex kg field, one for psi and another one for psi star. So these are the Lagrangian density for real and complex kg field. I have provided the Lagrangian density for the electromagnetic field in the notes given you in the PDF form. You should go through that notes and find the Maxwell's equation for electromagnetic field. Thank you.